Hi, welcome back to this video series on quadratic residues. In this segment, I will wrap up the discussion on Rabin Cryptosystem. In the previous segment, we talked about how Rabin Cryptosystem works. We found a limitation. We found a limitation in that system, meaning if you encrypt the same message, the information will be leaked about that. The message itself may not be leaked, but the eavesdropper would know the same message was sent. So that's because the encryption system has this formula that y is congruent to x square mod m, mod n rather. X is the message that Alice wants to send to Bob. So if she sends the same message x 2 times, the same y will come out. That's the problem. Okay, and we will fix it in this segment. We will make an assumption about n. N is basically a composite number made of two distinct R primes p and q. And there is one more property that p is equal to 3 mod 4 and q is also 3 mod 4. This is making it easy for us to compute the square root at the receiving end, like the Bob's end. Okay, so we talked about this, why we need this property for both p and q satisfy this property. Okay, not just p alone. So by the way, there is a name for this, Blum integers or integers of this structure, right? Made of two numbers p and q, prime numbers with this property. We will leverage that for this particular discussion. So the goal is to improve the Rabin system. We talked in the previous segment. We will introduce randomness. So the same X is sent, the attacker wouldn't be able to see it easily. That's the idea. So how do we do this? We will have to revise the definition of encryption a little bit to make this happen. And in this case, actually, the message is restricted to either 0 or 1. Okay, so if you have a longer message made of more than zeros and ones, of course, multiple zeros and multiple ones, what you have to do is you have to apply this multiple times. So the scheme is only secure for sending one bit at a time. Okay, that's basically the message. So the message space is basically 0 or 1. So how is the encryption going to work? Encryption is going to work as follows. The first step, let's say Alice wants to send a message m to Bob. M can be either 0 or 1, right, to Bob. So how is she going to do that? So what Alice is going to do is she first randomly generates a number x from z star n, the group that we are working with. So she randomly picks an element r, right, from z star n, this multiplicative group, right, and she computes, let's say, x, which is nothing but r square. So as you can see, x itself is a quadratic residue now because x is written as power of 2 of r, okay, some random number r, okay. And then she checks whether x ends with 0, okay. Suppose her goal is to send 0 to Bob. She checks whether x ends with 0. If it is, she will send not x as it is, she will send x square mod n to Bob. Okay, so this is basically what she's going to send to Bob. So Bob gets x square mod n. Everything is in mod n, so I'm not going to keep on writing this. So Bob gets y. What is Bob going to do? Now Bob's question is goal is to find x, right? So all Bob does is he applies the square root algorithm. From y he finds 4 possible x's. Remember, in mod n, for every y there are 4 possible roots. Okay, so he finds 4 roots. Now comes the question, how would he know which root to pick it up? So it turned out that because of this property that you have a p and q congruent to 3 mod 4, there is exactly only one square root of y that is also a quadratic residue. So let me explain this. So Bob gets the y, right? So how is the decryption going? Alice does the encryption and send y to Bob. So Bob gets the y, and he knows the n, he knows the n, he knows p and q. He generated the p and q. Okay, so what is Bob going to do with the y? Bob takes the y and he computes the square root of y in mod n. So we have seen how to do that. Okay, it will give Bob 4 possible answers. Okay, could be x1, x2, y, x3, x4. Let's call it like that way. So there are 4 possible answers to this. So x1 square will give him a y. X2 square will also give him a y. X3 square will also give him a y, and so is x4 square. So he doesn't know really which one to pick. For sure, one of these must be matching the x that Alice sent, right? So how is Bob going to select that? So here comes the neat trick. What Bob is going to do is going to compute the Jacobi symbol for each of these, right, in mod P as well as in mod Q. If the Jacobi symbol is 1, what can he tell? He can tell for sure that that particular element was the element sent by Alice, and then he will just go and pick the least significant bit, because remember, only zeros and ones are allowed in this system. Okay, so why is only one element among the 4 elements have the property that the Jacobi symbol is 1? That's because of this property that whenever you have P and Q 3 mod 4, and if you compute the square root of a number, you get 4 positives, you get 4 possible square roots. Among the 4 possible square roots, only 1 is a quadratic residue. So out of these 4, only 1 will be a quadratic residue, and that is exactly the element sent by Alice, because remember, Alice is basically sending a quadratic residue, right? He's sending x square with mod n, which is y, and Bob takes the y and he reconstructs 4 possible x's. Out of those 4 possible x's, he knows for sure there's only 1 that can be possible, because that's how the Blum integers work. This is the Blum integers, B-L-U-M, Blum. He created some interesting crypto systems and contributed to theory of computation. Okay, so his algorithm is basically the foundation for this particular integers, Blum integers. Okay, anyway, once you have this property P and Q being 3 mod 4, you take square root of y. The y is the incoming y Alice send. You get 4 possible square roots. Out of those 4 possible square roots, 3 will be thrown away, because 3 of them are not going to be quadratic residue. Only 1 of them is going to be quadratic residue. Okay, so that's the idea. So let me explain now and show you a basic demo. We have already talked about this actually, that only one of the 4 possible roots is also a quadratic residue. Let's say we are working with the group Z star 21. The second column shows that we have quadratic residues 1, 4, 16, right? These are the 3 possible elements, right? 1, 4, and 16. 1 is 1 square, 4 is 2 square, 16 is 4 square. But wait a minute, 4 also has other roots. 4 also has other roots. 1 is 2 square, 5 square is also 4 in mod 21. 16 square is also 4, and 19 square is also 4. But there's one more fact. Let's consider 4, for example. 4 has 2 square, 5 square. What are the square roots of 4? 2 square is 4. 5 square is also 4 in mod 21. You can check for yourself. And 16 square is also 4. And what is the final one? 19 square. But out of these 4 square roots of 4, okay, these are all the square roots of 4. Okay. 2, 5, 16, and 19 are square roots of 4. But if you look at the second column now, out of the 4 numbers that I have listed as square root of 4, only the number 16 occurs, right? 2, 5, and 19 do not occur as part of the column 2. That means 2 cannot be the answer, 5 cannot be the answer, and 19 cannot be the answer. These are the possible square root quadratic residues in the context of Z star 21. Right, and we are just playing with the number 4. Okay, 4 has, what are the possible square roots? 2, 5, 16, and 19. Out of those 4 possible square roots, only 1 is a quadratic residue. That is always true whenever you have your P and Q satisfy this property that P is equal to 3 mod 4, and Q is also 3 mod 4. Remember, 7 mod 4 is 3, and 3 mod 4 is also 3. So in this case, P is, well, we can easily see P is 3 and the Q is 7. Okay. So in such systems, there's, out of the 4 square roots, only 1 is a quadratic residue. Okay. And that one is the one that was sent by Alice. Because let's say Alice's goal is to send an even number to Bob. So she picked say 4, and 4 is a quadratic residue. So she sent 4 to Bob. What is Bob going to do? Bob is trying to find the square roots of 4. So he's going to find either it could be 2 square, 5 square, 16 square, and 19 square. And he throws away 2, 5, 19 because they're all not quadratic residues. So he's ending up with 16. And the 16 itself is basically an even number. So he will know that Alice was sending an even number. Similar reasoning can be done for odd number as well. Let's say Alice was sending an odd number 1 to Bob. By the way, the message is only 0 or 1. So we don't really know either it's some other number, but we're only caring whether the bit was 0 or 1. Let's say the bit was 1. What are the possible square roots of 1? We can see here the possible square roots of 1 are 1. 1 square is 1. 8 square is also 1. And what else? 13 square and 20 square. Okay, these are the possible square roots of 1. And again, we can convince ourselves that 8, 20, 8, 13, and 20 are not part of the second column. Therefore, 8, 13, and 20 can be thrown out. What you're left with is just 1, and that's exactly the one that we talked about, assuming Alice sent 1 to Bob. So this crypto system solves the problem of chosen plain text attack, because every time Alice wants to send a new message or even the same message, she's picking a random number X with certain property, right? The property is that the least significant bit of X is 0 or 1, depending on what she wants to send. That's how she's encoding that. Okay, let me now show you a demo of this, and then we will wrap it up. What you're going to see is my little implementation of this algorithm, right? And I will quickly show you what are things happening. Of course, this for demo purpose, I took a 512 bit. In production, you will be using 2048 or more. All right, so here is the encrypt function, right? Encrypt, what are we encrypting? Alice is encrypting a message 0 or 1 are the only allowed messages. And she's going to send some gibberish ciphertext to Bob. So Bob gets a huge hypertext. What is Bob going to do? Bob going to decrypt it, and he will get 4 square roots. We talked about finding square roots. So there are 4 possible square roots. And among the 4 possible square roots, he's going to compute Jacobi for each of those, right, in mod P and mod Q. And as soon as he gets Jacobi symbol value to be 1 for both mod P and mod Q, he knows that that particular root 1 is the root that he's interested in. And he computes the least significant bit. So he knows what was sent by Alice. So let me show you now. So Alice is sending 0. So we expect the program for Bob to say, I got 0. Let's try this. Let's try this. Okay, so you can see here, Alice sends some ciphertext to Bob, which is basically encryption of message 0, right? And Bob decrypts it to 0. So he got 0. Now let me show you what happens if I just change it to 1. Bob gets 1. So this is working. Okay, then and one more thing now. So what about encryption? Is it dynamic? Is it changing if you send the same message? Let me convince you that's the case. So I'm going to print the ciphertext, right? It's going to see, you see here, Alice sends some gibberish to Bob. Let's run this again. Now let me remember 2411 is just a number to remember. It should be hopefully different now. Yeah, it's 1675, so it's different. So every time you send the same message, you get a different ciphertext. So eavesdropper wouldn't know a 0 was sent or a 1 was sent. And so why is this dynamic? It's dynamic because of the encryption function, right? Alice wants to encrypt a bit 0 or 1, which is in this case A. A can be either 0 or 1. All she does is she generates a random number element, random element from the group Z star n. She then computes R square mod n, and then she checks whether this R square mod n is same as the bit she wants to send. If that is the case, she sends the square of that. So essentially, she's sending R power 4 to Bob, which is fine, because all Bob cares is does it end with 0 or 1? That's what he wants to figure out. So the X, remember, X itself is a quadratic residue because X is made of R square. Okay, so X is quadratic residue, no doubt about it. X is a quadratic residue, and X has an additional property. It matches the it has to match the bit that Alice wants to send. Okay, if Alice wants to send 0, the least significant bit of X better be 0. If it is 1, it be 1. That's the reason why this while loop is keep trying until that quadratic residue and the least significant bit of the X matches the number X, number A that Alice wants to send. A can be either 0 or 1. Okay, so we can make sure that it's just a 0 bit or 1 bit. Okay, the system only works 1 bit at a time. Okay, so that's one important message. And then the decryption process is exactly same as what we talked earlier segment, right? In the previous segment, we We take the ciphertext Y and we find the 4 roots and we send the 4 roots to Bob. Bob has to compute now the Jacobi of each of the roots, right? And make sure that both P and the mod P and mod Q, the Jacobi is 1, then he knows he got the right square root, and then he takes the least significant bit. That's the reason why you're seeing a %2. So that's basically the core idea of this Rabin